You've no doubt noticed that for many of the limits that we calculate, it turns out that we could save ourselves a lot of work just by plugging in the number where we're taking the limit. And often that gives us the same result as sort of calculating the limit the long way does. So here's an example of that. If we sort of do it the proper way by using the limit laws, it's a bunch of writing, and first we would use the difference rule for limits. So we get the limit as x goes to 3 of x squared minus 2 times the limit as x goes to 3 of x minus the limit as x goes to 3 of 4. This limit, we can then use the exponent rule for limits. So the square of the limit as x goes to 3 of x minus 2 times, and then this limit, that's 3. And the limit of 4 as x goes to 3, that's just 4. And now, finally, this limit on the inside is 3, so 3 squared minus 2 times 3 minus 4, that's 9 minus 6, so 3 minus another 4, that's minus 1. But if we just plug 3 into this polynomial at the very beginning, we get 3 squared minus 2 times 3 minus 4, and that's the same thing, that's minus 1. So, you can see both of these give us the same thing. And in this particular example, there's no real mystery why this happened. It's because the limit laws let us just sort of move this limit all the way to the inside until it sort of hits these x's. And then it just plugs in the 3, because the limit as x goes to 3 of x is just 3, because that's one of the obvious limits that we know. And this isn't the only, having a polynomial here isn't the only situation where this sort of thing happens, where evaluating the limit and plugging in the x value are really the same thing. So it's a good idea to, I guess, first of all, name this phenomenon, and second, make note of when exactly this phenomenon happens, because if we know that this is happening, it's going to be easier to evaluate the limit just by plugging in the x value. But to do that, we need to know ahead of time that that's okay. Well, first let's give this phenomenon a name. So the name that mathematicians have chosen is continuity. So we say that a function is continuous at some x value a if the limit at that x value is the same thing as the value of the function at that x value. That's just a long way of saying that what happens near a is the same as what happens at a. Right, so the value of the function at a, that's what happens at a, and then the limit is what happens near a. So saying that a function is continuous at a just means what happens near a is the same as what happens at a. The word continuous might not make a ton of sense at first, but if you kind of draw the geometric situation that this is describing, you'll see that the choice of the word continuous is it's a good choice. So suppose that we're in this situation where we have some function where the limit at a is the same as the value of the function at a. What would that look like? Well, here's a. And to have a function where the limit at a exists, that means that there's going to be some limit value, and near a, the function sort of heads towards that limit value. But if this limit value is equal to the value of the function at a, that means that this spot right here is actually part of the graph. So the graph, connects up as you cross through the point A. In other words, as you go through the point A, you can draw the graph without lifting up your pencil. And in other words, the graph is one continuous piece here at A. And that's why we use the word continuous. So now that we have a definition for this, or a name for this phenomenon, and a definition that we could check, let's go back and look at some common types of functions to see where they are continuous. And when I say common types of functions, what I'm intending, at least at first, is polynomial functions and rational functions. So let's think about polynomial functions. A polynomial function is going to look like this. So it has some degree n, and it has a bunch of coefficients. Those are all the b's. The b's in this case are all constants. and x is the variable. So the domain of any polynomial is all real numbers. So what we could ask ourselves is, for any real number a, is this polynomial function f of x continuous at a? Well, we can check if it's continuous at a just by checking the definition. We can calculate the limit as x goes to a of f of x, and we can compare that to the value of the polynomial at a. Well, the value of the polynomial, all we need to do is plug in the value a. So we get b sub n, a to the n, plus dot dot dot, down to b sub 0. Now we need to find the limit for f of x as x approaches a. Well, since a polynomial is a big sum of terms, we can start out just by using the sum rule for limits. So we get the limit as x goes to a of b sub n x to the n plus, and then the limit of the n minus 1 term, and so on, all the way down to the limit as x goes to a of b sub 0. Right? We want to check, are these the same? Well, for all of the terms other than the constant terms, so for all of these terms here, they all have a constant inside, a constant multiple, so we can move the constant multiple outside of the limits. That's one of the limit rules. And then we can move the limit inside this exponent. That's another one of the limit rules. So what we get is b sub n times the limit as x goes to a of x to the nth plus, and then the same thing for the n minus first term, and then same thing for the n minus second term, all the way down to the limit as x goes to a of b sub 0. And now this limit is one that we know. That's just a. So this is b sub n, a to the n, plus, and then the same thing will happen in the n minus 1 term. So we'll get b sub n minus 1, a to the n minus 1, and so on, all the way down to this last one, the limit of b sub 0. Remember, b sub 0 is just a constant, so that's b sub 0. And we were going to check, is it the same as this? Yes, those are the same. So the upshot of all of this is that all polynomials are continuous for every real input. And that's really nice to know, because now that we know that, if we ever want to calculate a limit of a polynomial, we know ahead of time that we can just plug in the x value. We don't have to mess around with the laws of limits, because we know already that polynomials are always continuous. So if we wanted to calculate, for some reason, the limit as x goes to 2 of x squared plus 3x minus 4, we don't need to mess around with the limit laws. We know ahead of time this polynomial is continuous at the x value 2, so it's safe to just plug in 2. We get 2 squared plus 3 times 2 minus 4, and that's, what, 6 plus 4, 10 minus 4, 6, right? So you can see, if you know that your function is continuous at this x value, calculating the limit is trivial. You just plug in the x value. All right, so that's for polynomials. What about for rational functions? Well, rational functions are just ratios of polynomials, right? A rational function is a fraction where the numerator is a polynomial and the denominator is a polynomial. The one tricky thing about rational functions is that rational functions, their domain might have holes in it. So, right, because anywhere the denominator is 0, that's a hole in the domain for your rational function. So let's suppose that we have an x value a real x value a, where the denominator polynomial q isn't 0. Okay, and let's check if, let's ask ourselves, is this rational function continuous at a? Well, we need to compare the limit as x goes to a of f of x. We need to check if that is equal to f of a. Well, f of a, that's just p of a over q of a. And this makes sense because we know ahead of time that q of a isn't 0, so we are not dividing by 0 here. So now let's work on the left-hand side of this. Let's work on the limit. Well, this is the limit as x goes to a of, well, f of x is just p of x over q of x. All right, but look, now we have a quotient, and the limit rule for quotients says that the limit of a quotient is the quotient of the limits, as long as the denominator isn't 0. So we can write this as limit as x goes to a of p of x over the limit as x goes to a of q of x. And this is true, right? These two things are equal as long as this denominator isn't 0. So we'll have to check that this denominator isn't 0. It won't be, but we have to check. All right, so what about the numerator? Well, notice in the numerator we're taking the limit of a polynomial. We already know that polynomials are continuous everywhere, so we know ahead of time that it's safe to just plug in this x value. So the limit in the numerator is p of a, but then the same thing goes for the denominator. The limit in the denominator is q of a. And notice that we assumed that q of a is not equal to 0, and so it was safe to use the quotient rule for limits here. All right, and now comparing these two, we see that the limit is the same thing as the value of the function. So the upshot of this is that all rational functions are continuous for all x values a where they are defined. All right, so for polynomial functions and rational functions, if we have any limit involving a polynomial or a rational function, it's safe to just plug in the x value. For rational functions, if you get a 0 in your denominator, then that's just telling you that the x value you started with wasn't in the domain to begin with. All right, so armed with this, we can actually make short work of many limits, even limits that aren't dealing with polynomials or rational functions directly. Let's look at a couple examples. Okay, so for our first example, let's figure out if this function is continuous at x equals 4. I'm sure that I meant for this to say 4 and not 1. Let me just change this to 1. That's going to be the best way to fix this. Okay, well, this is a multi-part function, right? So when we compare the limit as x goes to 1 of f of x, when we compare that to the value of the function at 1, right, for the part on the right, well, that's just f of 1, right? This multi-part function says that when x is 1, the value of the function is 1 over 4. So the right-hand side here is 1 over 4. But for the left-hand side, remember, since we're taking a limit, the x value that we're referring to here is not 1, right? It's close to 1, but it's not equal to 1, right? The limit is asking what happens as x gets close to 1, but not equal to 1. So for this appearance of the function f of x, we know that x isn't 1, and so we can use this, this formula from the multi-part function. So we're taking the limit as x goes to 1 of x minus 1 over x squared plus 2x minus 3. Okay, we want to check if these are equal. Well, this is a rational function, so what we can do is just plug in our x value. But if you do that, what we get for this example is 0 over 0. So remember, rational functions are continuous wherever they're defined, but this particular rational function is not defined at x equals 1. So we have to work a little bit harder. But remember, we have some algebra tricks for dealing with this kind of situation. We can factor the denominator. So this is the limit as x goes to 1 of x minus 1 over, so the denominator factors, it's x minus 1 times x plus 3. And now we can simplify. And the stuff that's left here is a rational function still, but now it's defined at x equals 1. So we know that it's continuous at x equals 1, so now we can just plug in our 1. We get 1 over, let's see, 1 plus 3, that's 4. And that's what we were hoping to get, right? 1 over 4 is equal to 1 over 4. So this function is continuous at x equals 1 because the limit at 1 is the same as the function at 1. You might wonder what's going on with the graph of this. Well, this rational function, right, it has, so let's see, I guess it's going to look like it has a vertical asymptote at minus 3. Yeah, so it looks something like this, but it turns out that at x equals 1, it has a hole, right? And what this multipart function does is it just fills in the hole, right? This hole is at height 1 over 4, and so you can make this function continuous just by filling in that hole. And that's what this multipart function is doing. This multipart function, most of the time it's this rational function, but then when x is 1 at the hole, it just fills in the hole. All right, let's look at another example. How about this one? Is this function, g of x, continuous at x equals minus 2? Well, again, we're just going to check. We're going to calculate the limit as x goes to minus 2 of g of x. And we're going to compare that to the value of g of minus 2. And I see I've forgotten a minus 2 right there. Here we go. All right, well, as usual, evaluating the right-hand side is the easy part. G of minus 2, this is a multipart function, and it tells us to use the second formula when x is minus 2. So we get 1 here. So now let's evaluate the limit on the left-hand side. On the left-hand side, we're taking the limit as x goes to minus 2. Now again, this g of x, since we're taking a limit at minus 2, this g of x can't be minus 2, and so that means we're using this line of the multipart function. So this appearance of the function g of x is really just 1 over x plus 2 squared. All right. Now this rational function isn't continuous at minus 2, so we can't just plug in the minus 2. Instead, we have to think about what happens to this function as x gets close to minus 2. Well, you know, this 1 over x plus 2 squared, this is just a shifted version of 1 over x squared. And we know what 1 over x squared looks like. It looks like this. And so 1 over x plus 2 squared looks the same, except it's been shifted to the left 2. So it has this vertical asymptote at minus 2, like this. Well, looking at this extremely quick sketch of the graph of 1 over x plus 2 squared, you can see that the limit at minus 2 is plus infinity. All right, so to check continuity, we're asking, is this limit the same as the value of the function? And clearly the answer is no in this case, right? So this function, it looks like 1 over x plus 2 squared, except at minus 2, it has a value 1. And you can see that this graph isn't continuous. You couldn't draw this graph without lifting up your pencil, because you have to lift up your pencil to move from this part going up to infinity down to the point that's at minus 2. So is this continuous? Definitely not. All right, one final example. Let's check on the continuity of h of x, which is this multipart function, at x equals 1. This time we have to be a little more careful with the limit because of how the inequalities are set up. So again, we're going to calculate the limit as x goes to 1 of h of x. We want to compare that to h of 1. And it looks like h of 1 is just 1. All right. Well, for a multipart function, right, this multipart function uses a different formula on each side of 1. So to figure out what the limit is, right, we can't use a single formula like we did in the previous two examples. So what we'll have to do is break this into two limits, each on one side. So we'll calculate the limit as x goes to 1 from the left, and we'll calculate the limit as x goes to 1 from the right. Right? Because we know if these two one-sided limits are the same, then the two-sided limit exists. So let's calculate the one-sided limits. Now for the one-sided limit on the left, right, approaching 1 from the left, all these x values are less than 1, so we'll use this first formula for h of x. So here we're finding the limit as x goes to 1 from the left of x, but that's 1. For the limit from the right, here these x values are all bigger than 1 since we're approaching 1 from the right. So this is the limit as x goes to 1 from the right. Right, for x values bigger than 1, h of x is just 2x squared. And 2x squared is a polynomial. So we know that since it's a polynomial, it's continuous at 1, so it's safe to just plug in this x value. And we get 2 times 1 squared. That's 2. Well, these two one-sided limits, these are different. And since these two one-sided limits are different, that means the two-sided limit does not exist. Since this two-sided limit doesn't exist, it can't be equal to 1. So this function is definitely not continuous at x equals 1. The function itself is defined, but the limit at 1 doesn't exist. If we sketched a graph of this multipart function, you would see why that is the case. So let's see, for x values less than or equal to 1, it just looks like y equals x, like this. But to the right of 1, it looks like 2x squared, and it turns out that that looks like this. And clearly, this isn't continuous at x equals 1 because there is no, you can see there is no limit because the one-sided limits are different. And so the limit can't be equal to the value of the function.